Hello, my friends. Welcome to Thermal Engineering Concept and Principle. How can we determine the dimensions of geothermal vertical heat exchangers? This is the objective of the present episode. Come with me and let us go deeply in this subject with Professor Ali Tarad. Hello, everybody, and welcome to Thermal Engineering Concept and Principle channel. We will continue to introduce the subject which is related to the heat transfer treatment for geothermal application. Let us describe it for the objectives of modeling of the borehole thermal design, and here we will take the opportunity to talk about the thermal design of the single and double U-tube applications. Let us talk about the concentric equivalent diameter technique, which will be used to describe the U-tube heat exchanger, which is usually in a vertical orientation. Let us start with the objectives of the present episode. The main objectives of our present video is related to the single tube heat exchanger and the concept of concentric tube in model number 1 and the same thing in model number 2, which will be described in the present video, and then we will take a case study, an application in industry for the DX heat exchanger, and finally we will arrive to the closure for this episode. How to estimate the borehole depth? Let us consider a model where we have a U-tube as shown in figure A is transformed to single offset tube that is called eccentric arrangement as shown in figure B. Then we would like to have a transformation of the offset tube to a tube that is concentric as shown in figure C. Here we will depend on the derivative which should be followed to obtain an arrangement to show that the resistance of an offset tube R sub off equal to 1 divided by S sub F K sub G, where K sub G refers to the Groot thermal conductivity and S sub F is presenting the shape factor of an eccentric tube that is shown in figure B. We have also a concentric tube where it has an equivalent diameter, and this resistance is referred to R sub E equal to 1 divided by S sub E K sub D. And we have S sub E, the shape factor of a concentric tube in a cylinder. It is represented by S sub E equal to 2 pi L divided by natural logarithm of D sub B, which refers to the bore diameter, divided by D. For a constant thermal resistance of the offset and the concentric equivalent tube, we will get that the shape factor is equal, and that will lead to D equivalent in the term of D sub B divided by x plus square root of x squared minus 1, as shown in equation number 6. In this equation, we have x is presented in terms of borehole diameter, tube diameter, and the tube spacing distance, as shown in equation number 7. The derivative for this model is presented in a reference as shown here, and it will be the first of references in a list that will be included in the description box below this video. The single concentric U-tube equivalent diameter technique for model number 2. Let us consider a borehole with a single U-tube as shown in this figure, and it is to be designed for the sizing purposes of the depth for this heat exchanger, and we will transfer it to an equivalent tube to be corresponding and representing the single U-tube in a concentric tube with the borehole. The first step is to assume that the volume of the grouting material is constant, then that will yield the equivalent equal square root of 2 times D naught. And we will introduce another concept that to keep the surface area of the original design and the equivalent one to be constant and equal, then we will end with the equivalent equal 2 times D naught. If we take the average to include both effects, then we will find that the equivalent diameter equal to square root of 3 times D naught as presented in equation number 1. And the grout or fluid filling resistance is represented by a concentric two cylinders as shown in this figure, and R sub F equal natural logarithm of D bore divided by D equivalent, all of that divided by 2 pi K sub G, and K sub G represents the thermal conductivity of the grouting material. And we have the RP, which should be kept constant as well, which is composed of two components. The first term on the right-hand side represents the convection part as a result, for example, for the condensation of the refrigerant which passes through this heat exchanger, or maybe we are dealing with water which passes through this tube, or brine. So this is the convection part plus the conduction part through the tube wall itself. Then we will arrive to R sub B equal R sub F plus R sub P as represented by equation number 4, and all of that is described in this reference, which can be found in the list below the video in the description box. Let's take a case study where a heat pump, which is a geothermal heat pump, uses a condenser in a sort of DX heat exchanger as part of this heat pump. It is used to cool down a place such as a room or a store or a domestic place, and the condensation heat transfer coefficient is for Freon R410A, correspond to 3000 part per meter square degree centigrade, which is a typical value is used in this application. And let us deal with a single U-tube as shown in this table, made of copper tube, and both ascending and descending legs of the tubes are an equal diameter, and the thermal conductivity for this metal is 400 watt per meter Kelvin. And we will go through this application for this geometry for a range of thermal conductivity of the grout material, range between 0.73 watt per meter Kelvin up to 1.9 watt per meter Kelvin, as shown in this table. And if we need the ground thermal resistance, it will correspond to 0.053 meter Kelvin per watt, where the ground thermal conductivity is equal to 2.42 watt per meter Kelvin. These information will be used to design this geothermal DX heat exchanger. If we want to design the heat exchanger, let us go through the effect of a grout thermal resistance for the model number 1, which is the offset to concentric equivalent diameter technique that is described in reference number 1. Here we have WF equal 14.29, and the results are compared with other investigators that we have the maximum value is for both etal, and the minimum value was predicted by Sharkawi etal, and it's obvious that the grout thermal resistance is ranged between 0.31 to 0.16, almost double the value. Therefore, we have to take an attention when we want to select the proper equation to predict or to calculate the uh, thermal resistance of the grout material, and it seems from this curve that all of these behaviors have the same trend, and as the thermal conductivity increases, the thermal resistance decline or comes down, and here we have uh, Tarad 1, which is represented by model number 1, is almost nearby the maximum value predicted by both eta. For the same geometry, here we have the total thermal resistance, and again it indicates that the maximum was predicted by both et al, and the lower value was predicted by Charkawi. And these values dictate that an attention should be paid before selecting the equation to be used, because this total resistance will reflect the heat loading of the heat exchanger, and that will give the depth of the heat exchanger. So as the thermal resistance goes down, it means that the depth of the heat exchanger will be lower, and as the thermal conductivity increases, then we have to select a proper equation as well to predict the total thermal resistance, which is reflected on the uh, depth of the heat exchanger. Here we are using the average concentric equivalent diameter technique as described in reference 2. And again here, the maximum was predicted by both et al, and the minimum was predicted by Raymond. And our model, the number 2, is presented by the um, black solid line, Tarad 2, almost occupy the mid distance between the maximum and minimum. And we have to mention that all of these curves are close to each other. And but again, we have to mention that our focus should be goes in the direction of selecting a proper equation, and all of these correlations predicted the same trend for the grout thermal resistance, and as the thermal conductivity of the grout increases, then the thermal resistance will be lower. And for this correlation, the difference between the upper and lower is not that much as the one which we described in reference number 1, and this could be selected as well for a preliminary design of geothermal heat exchanger as well. Here we have the total thermal resistance as predicted by model number 2. And again, it's the same behavior as described by the model number 1. We have the same trend for these curves, and as the thermal conductivity of the grout material increases, then we will get a lower total thermal resistance, which is uh, related directly to the depth of heat exchanger required for a specific heat duty as well. Dear friends and colleagues, we arrive to the final part of this episode, that is the closure. We passed through the modeling process of geothermal heat exchanger, which is described for the vertical borehole, and we used the uh, equivalent uh, diameter technique in the sizing and specifying the dimensions of the geothermal heat exchanger. Uh, then we applied a case study uh, for the application of the models described in this episode. We have some useful references. You may find them at the bottom of this video in the description box. And uh, thank you for listening. And at the same time, I urge you to subscribe and share what we have in the YouTube channel with your friends to achieve the main goals of creation of this channel, and see you in the near future. Bye bye.